Uh, we'll start now. So, good evening, all the participants from who have joined this AICTE 6-day online faculty development program. And today's speaker, Dr. Rishikesh Gade sir, on behalf of Maharishi Karve Stri Shikshan Sanstha and Cummins College of Engineering for Women, I welcome all the participants for the day 3 and fifth session on nanomaterials. This is in sequence third day of this faculty development program. Today we have with us Dr. Rishikesh Gade. Let me take a privilege to introduce Dr. Gade. Dr. Rishikesh M. Gade has been an assistant professor at MNIT Jaipur since June 2020. Before joining, he worked as a postdoctoral research fellow at IIT Bombay. Upon completing his doctorate from VNIT Nagpur in 2019, he obtained his BE in Chemical Engineering from BITS Pilani in 2012 and Masters in Chemical Engineering from ICT Mumbai in 2014. He also has an industrial experience of 1 year as a process engineer at a Solvay Specialty Polymers. His core research area is based on molecular dynamics simulations, which have primary applications in novel materials development. His collaborative and independent projects dwell into the applications of dual eutectic solvents, developing novel solid oxide fuel cell materials and PLA-based systems, and integrating machine learning and artificial intelligence in the material innovation. His work is geared towards developing materials with a novel uh, physiochemical properties for diverse applications spanning biomedical and chemical industries and environmental pollution control. He has in total published 9 peer-reviewed research articles in international journals of repute and several conference publications. He is currently guiding one PhD student and already completed his guidance for 3 masters and several UG level projects. He has taught courses such as Advanced Process Control, AI/ML in Chemical Engineering, Applied Statistics for Chemical Engineers, Bioprocess Engineering, Fuel Cells, and Non-Conventional Energy Sources. So, with this diverse and advanced area, we have Dr. Rishikesh for today's session. I welcome you, sir. And
Thank you, Prasannaji, for your introduction and this opportunity to deliver in this 6 days faculty development program AICTE sponsored. So what I will do, I will share the screen, I will share the PPT, and then based on PPT, I will proceed with my lecture.
okay, sir, no problem. Thank you. Nikhil, you please stop your shares. Okay.
So
Yes, sir.
I suppose my screen is visible.
Yes, sir. Visible. It's visible.
So in case if there is some technical issues, please let me know, Prasanna ji. So in case if I get muted or if there is net connection issue or something, you can call me. That's also not an issue.
Okay, sir. No problem.
So I will start with my PPT. So good evening to all the
Sir,
participants. Yes.
sir, do it in slide mode.
I have done it in the slide mode. Is it not visible in the slide mode?
No, no, no.
Uh,
Slideshow. Make it slideshow.
now?
No. You please close this and
Okay.
you share your screen. Oh yeah, yeah. Now do it.
Now?
Nine.
Okay.
Do one thing. You close this.
Closing.
Yeah. or stop it and again share it, because now your video is there.
Now I will share.
Okay.
And so should I share entire screen? I will share the entire screen. That should be okay. Now I suppose it would be visible, PPT,
PPT is visible, but not in a slideshow.
not in slideshow.
Yeah, now, yeah. एकदा करा अजून परत. हा, आता आलाय.
Yeah. Okay.
आता आलाय.
So, okay. Now I'm audible and screen is visible in PPT format, right?
Yes.
Yes. Okay. So thank you. So welcome all the participants. Good evening to all. So this particular FDP, which has title 21st Century Materials, Advancements in Material Science and Technology. So jointly organized by Cummins College and ASM International Pune chapter. So I have been given topic to be explained, which is based on nanomaterials. And my core research area is based on molecular dynamics simulations. So what I thought, like, I would explain how molecular dynamics simulations can be used for nanomaterials development, and why, especially in 21st century. So there are certain reasons why we could harness molecular dynamics simulation techniques, especially in the field of materials development, and that too in the 21st century. In that particular lecture, I would try to cover up certain topics. Like, first, I would explain playing role and which was not there before the starting of this particular era.
Sir, sorry to interrupt.
Yes.
You please switch off your video because your voice is, I think, interrupting.
Just a second.
हा, व्हिडिओ बंद करा म्हणजे बरं होईल थोडस.
Now,
नाव इट्स फाईन. मधात आवाज ब्रेक होत होता.
yes. Now my voice is in continuation.
Yes, sir.
Okay, thank you. So I have divided my presentation into certain contents. So first, I would explain why in this particular era, computational advances are playing a role in material science development, especially. Then coming to, because many of us may be new to this particular technique, many of us may be fundamentally experimentalists, and many of us may not know what is molecular dynamics simulation. So in very brief, I will explain what is molecular dynamics simulation. Then certain applications of molecular dynamics in especially nanomaterials domain. Molecular dynamics has wide application, like it is applicable in civil engineering domain, mechanical, chemical, biochemical, all materials development domain. So it's a very widely used domain, but in that specifically domain, I would be explaining the applications of molecular dynamics in nanomaterials domain. So again, Prasanna, if in case if there is some problem from my side, please interrupt.
Yes, sir.
And let me know. And if it's going fine, then fine. But in online mode, we don't know what's going on in that side. So in case if there is some, you please feel free to interrupt and let me know.
Yes, sir. Yes.
So along with molecular dynamics simulation, there are certain other complementary computational techniques. I will briefly mention about those techniques. Some of the case studies which I have published. So I would briefly explain 5 case studies, which are on my own studies. So my main motive in explaining those case studies would be to show like how molecular dynamics simulation is a versatile tool, and what different kinds of analysis and insights we can get from molecular dynamics simulation, which are very relevant for nanomaterials development. And then we can have certain discussion, what are the challenges, what are the opportunities, what can be done in terms of molecular dynamics simulation. So I will keep sufficient time for that particular discussion. So in case if there are certain questions, you can have a note and we will discuss those at the end. We will have sufficient time. So first question, can computational approaches propel the future of nanomaterials development? So till this particular time, when we didn't have sufficient amount of computational technology, so the majorly all the experimental or the materials design is a domain of experimentalists. Like you will have laboratories, you will perform certain experiments, you will develop certain novel development. Till date was the criteria, but now with advancement in computational techniques, with like availability of fast supercomputers, now that particular thing can also be done on computer. So you can think of certain materials which you think, okay, this particular combination of materials can have these particular properties, and using different computational techniques you can predict whether whatever you are thinking, whether that's correct, incorrect, can that be modified, can there be something which can be done in terms of materials development. So with availability of computational techniques and tools, now in this particular era of 21st century, molecular dynamics or computational techniques can be very relevant in terms of materials development, in addition to experimental techniques which have been traditionally used as the way to develop novel materials. Now, very basics of molecular dynamics simulation. What we do in molecular dynamics simulation, so basically we calculate certain average microscopic properties and then we correlate with the macroscopic observable properties, because all the macroscopic observable properties that we look at in bulk, that's basically originate from the microscopic properties. So if we have the holdover microscopic properties, we can certainly predict macroscopic properties. So that's what we do in terms of molecular dynamics simulations. Also, in terms of experiments, there are certain limitations. Like we have limitations of time scale and dimension. We cannot look below certain dimensions without certain specialized instruments. Also, let's say if we try to perform certain very high temperature experiments, very low temperature experiments, there are certain limitations in terms of experiments. But if we could translate those particular things into simulations, obviously we can have idea about what happens in those particular conditions. So that's particular one of the area where computational techniques come handy. So simple definition of molecular dynamics simulation: computer simulation of movement of atoms and molecules. That's a very basic definition of molecular dynamics simulation. Okay, certain applications of MD simulations. As I said, there are many applications of MD simulation. I'm just briefly presenting few of the applications. So like one of the application is to getting insights of biomolecular activity. Second could be getting insights of biomolecular association. It can be computational drug design. So all these three examples which I have shown, these are primarily in terms of biomedical field. Okay. Then there could be molecular simulation of ionic liquids, or it could be study of melting of ice under high pressure. Now, if you look at this particular study of melting under high pressure, experimentally, you will need very sophisticated devices to study those. But let's say you have a hands-on molecular dynamics simulation and you have sufficiently developed computational tools, you can have those particular things done on the computer. So you won't need much of the sophisticated experimental setup, but that can again be done at very good precision. Okay. Then exploring certain physical phenomenon at molecular level. So let's say that's a droplet and it is getting destroyed. So what happens in terms of picosecond level, that can be also done in using molecular dynamic simulation. Okay. So along with molecular dynamic simulation, so when we say molecular dynamic simulation, basically we consider atom as a rigid sphere. And considering that atom as a rigid sphere, we look at the association of molecules with other
Rishikesh sir, your voice is.
Detailed calculation of atomic structure, but the like disadvantage, your system size would get smaller. Then there could be molecular mechanics or quantum mechanics calculation, again allied with the DFT technique. You go inside the atom and you further explore the atom at the cost of loss of size of the system. So these are certain allied techniques. All of them are computational techniques and they have their own specific domain of application. My own expertise comes into the molecular dynamics simulation. So I would be presenting certain case studies which I have performed in terms of molecular dynamics simulation. Now, because our time is relatively short and like the case studies, these are 5 publications. So in total, that's around work of 4.5 years. So I would be summarizing the applications. And again, I say my intention in this particular talk is to make audience aware about possibility of molecular dynamics simulations and its versatility about exploration. So in case if you miss certain things about certain studies, need not to worry. Papers are published, you can go through them, but you can just glance through like, okay, how wonderful this particular tool and up to what depth this particular tool can provide you the knowledge about system. So that would be sufficient. I would try to explain the published studies. So 5 studies I would be trying to explain. These are the names, they would be further explained further. So in total 5 studies I would explain. Now that's the first study which I will explain. That's basically the carbon nanotube graphene curvature inducement. Okay, so and what are the things which I am trying to explain through this particular study is like using molecular dynamics simulation, we can gain molecular level insights into feasibility, solvent effects, and thermodynamic drivers for self-assembly in CNT graphene nanostructures. So let's say you target to make certain nanostructure which is based on CNT and graphene. Okay. Now, what are the things which you will need to know? First thing that you will need to know, what should be the surrounding. Then what is the role of surrounding in that particular nanomaterials development? What size of nanostructure should be taken? Can any random graphene sheets be taken? Or what would be the driving force for the self-assembly of those particular structure? Okay, so there are a lot of the things which a material development person would be needed to know prior to even start experimenting with those particular things. So in this particular project, what we took a carbon nanotube, we took a graphene sheet, and we check what happens when they are allowed to interact amongst themselves in a water mediated environment. Okay, so there are different combinations of CNT graphene we try to simulate, and in one of the combinations we found that a CNT was wrapped around by the graphene, and you can see the structure which is very similar to the multi-walled carbon nanotube. Okay, so our basic theme was to see the structural changes in CNT graphene hybrid structure, so that then we can have a certain glance of what are the feasibilities, what are the possibilities in terms of development of nanostructures based on CNT graphene. So that's a very basic glance we wanted to obtain. So this particular thing, which is based on self-assembly, so I will explain details of this particular study. Okay, so this is our simulation system. So in all the 5 studies, there would be first the objective, like why we try to explore, and I will try to correlate it with the nanomaterial development very specifically. I will explain what are the simulation details, certain results, and then certain basic conclusions that we got through those particular studies. All 5 of them are published studies, and you can go through the research papers. These are available. So that's a simulation setup. So when we say GAF, it may be a very new term for the audience. It's a generalized amber force field. So when we say molecular dynamics simulation, when we say a molecule, basically it would be having certain atoms. Those atoms would be having atomic size. They would be having charges. There would be atomic bonds, bond strength, dihedral angles. So there is a particular term which is called as force field. So when we say gap, it's a generalized amber force field. There are thousands of force fields which are available, and those force fields are now very well developed. So, like if you have those force fields applied on your molecules, and if you obtain certain properties, you can be very sure that these particular properties are very well in line with the experimental observations. Okay, so over the period of time, there has been a lot of efforts and lot of force fields have been refined, and very well developed force fields are available. So that's a generalized amber force field which we have used. We have taken one of the carbon nanotube and graphene, solvated them in water. So there are certain technical terms, like the water may be of different kinds because it's a model of water. So you can have different kinds of water. We have chosen this particular model of water. Simulation run for 10 nanosecond, 300 Kelvin, 1 bar. 10 nanosecond may be a very short time scale, but that's what the things happen at molecular level. So in terms of molecular level, 10 nanosecond is a sufficient time interval. Obviously, temperature of the surrounding, normal atmospheric pressure. Okay, then interesting thing that we observed, that the graphene CNT which was kept nearby, they formed a multi-walled carbon nanotube like structure, and interestingly their separation was same as multi-walled carbon nanotube structure. So this particular observation, interesting observation, gave us further insight. Okay, then we will try to explore what are the details, and those then can be generalized for other CNT graphene based structure, or even for the other structures. So then we calculated what is the potential of mean force. Now again, this term seems very different, but those who are from mechanical background, those who have knowledge of thermodynamics, we know there is a basic principle which is called as free energy change in the system. So Gibbs free energy change. Basic criteria: if Gibbs free energy change of the system is negative, we say the particular happening to be favorable, and if it's a positive thing, we say that particular thing to be the negative. So in molecular dynamics simulation, there are calculations which are called as potential of mean force calculation, and these potential of mean force calculation give you the free energy change in the system. So now, as we said, we observed that the graphene rolls around carbon nanotube. So we were interested, okay, so whether it's a favorable change, obviously, because that's happening, that's a favorable change. Then what's the strength of that favorability? Okay, that's the first thing. Then other questions: what drives that particular association? Now, because these are hydrophobic substances, so whether they are getting forced by water to be around themselves, or they are forming that particular structure because of their own interactions. Now, when we come to materials development, these particular things are very important, because, like, let's say water is favoring them for association, we cannot have then different solvent in terms of material development. But let's say they are being driven by their own association, then we can think of other solvents depending on the experimental conditions. So these all details can come handy in nanomaterials development. So that's the first calculation that we did. We tried to calculate what is the free energy change when the wrapping occurs. So if you look at this particular graph, so this particular x-axis shows the difference between the graphene position and the CNT position. And as the graphene sheet comes into contact with carbon nanotube, how that particular energy of the system changes. So at this particular entire wrapping structure, it has very lower energy of minus 14.5 kilocalorie per mole, which is negative, and as per the Gibbs free energy criteria, it's a favorable change. That's the first observation that we obtained. Then what happens? So obviously, when CNT and graphene are coming into contact, there is increase in the number of atomic contact, and there is detachment of water molecule. Now, this may seem to be very obvious, but again, it has a very long significant impact in terms of material development, because, as I said, this particular thing guides the role of solvent and the structures in their cell assembly. So, so how that particular thing affects, that was further analyzed. Like when we say the association of CNT and graphene, so basically that particular entire association results from the interactions between CNT, graphene, CNT graphene and with the solvent contribution. So what is the individual role of these particular entities that was explored? So first thing that was observed, so this particular graph shows the segregated interaction, like the first interaction that we seen, that's between CNT and graphene, the red line. Okay, so this particular line shows like that's a favorable interaction between CNT graphene, and this blue line shows there is a unfavorable interaction between the due to the water or the solvent. So role of solvent is here obtained to be opposite to what is traditional effect. Like if let's say it was traditionally an hydrophobic event, water solvent molecules would have forced CNT graphene to be in their association. But this is not what is happening. They are getting associated because of their own interaction. That's the first observation that we did. Second, what happens in between the CNT and CNT graphene interactions? So their van der Waals interactions increases, which is very obvious because if atoms are coming into contact amongst themselves, van der Waals interaction would be increasing. Another thing which would be happening, because now the graphene which was flat in nature, now because it has twisted, its dihedral energy is going to increase. Now, why all these analyses are coming into picture? Because if we, let's say, look at the particular phenomenon of graphene sheet rolling around carbon nanotube, so that's a mixture of different phenomena. So CNT, which was surrounded by a solvent molecule, when graphene sheet approached it, firstly, the solvent molecules got differed from the CNT surface. That's the first thing which happened. Second, then the graphene sheet rolled, then increasing its dihedral energy, increasing the van der Waals contact area. So all these particular forces drive the interaction of CNT and graphene. So now when we have explored these particular forces, we can certainly comment upon certain things like, okay, what may be the criteria for their association? Like, can the size of that particular CNT guide? So let's say if CNT is very small, and if CNT is very small, then it cannot have such amount of van der Waals interaction, which can then increase the dihedral energy of graphene. Then such kind of CNT would be unable to roll the graphene. So these are the certain observations which we could obtain from this particular study. So basic conclusions that we obtained was, so this particular study is very specific for curvature inducement. Now again, if I try to correlate with today's topic, the molecular dynamics simulation in this study has provided us about the thermodynamics of self-assembly. It has provided us with the guiding forces which is driving self-assembly. It has provided us with the role of solvent which is driving that self-assembly, and certain more molecular level details which is guiding the association of CNT and graphene. So then these particular outcomes we can certainly correlate in somehow with the like the experimental findings, or let's say we can correlate with the development of nanomaterials which are based on CNT and graphene. So there would be a certain role of these particular outcomes in the nanomaterials development. Second study which I will try to explain, that is the capture of alkanes in the capped carbon nanotubes. Both these materials we know very good. These are very natural materials. CNTs we know when they are in the form of capped shape. These are called capped. CNTs, alkanes we all are aware of. So why this particular study? It may seem to be a very obvious study, but again, this particular study can provide us with very good understanding of conformational changes upon encapsulation within host structures with potential applications in designing nanodrug carriers and oil spill capture system. Two of the applications I have cited here in terms of materials development. Let's say you wish to form a capsule, okay, and that particular capsule needs to deliver a certain drug. Now, there are certain questions which would obviously arise. Can any capsule be used to capture any of the drug? Is it the possibility? Or there are certain restrictions on the material which can be used for capsule making. What should be the size of capsule? What should be the shape of capsule? What should be the shape of drug it can deliver? So that's a very basic question for the researcher who is working in the area of nano drug development. Okay. Second, let's say there is oil spillage. So I'm citing two examples, but you can correlate with many of the examples which you can correlate it with. So let's say there's oil spillage and you need to capture alkane in certain material. So can this particular CNT be used for that particular capture? So these are the two applications which you can correlate with this particular study in terms of materials development. Okay, so that's again a published study. So as I explained, this particular study correlates majorly with the biomedical application in terms of drug design, in terms of protein encapsulation. So if some of you is from biological background, if you remember, proteins are very specific to their conformation. So let's say if you change the conformation of protein, its property changes. Okay. So there are certain structures which are used to guide the folding of protein. Okay, so this particular study can again be correlated with those particular materials which can be used to guide the folding of protein. Now, when you say folding of protein, there are certain questions which need to be answered. So, what kind of protein would be folded? Whether it would be folded from ends, whether it would be folded from center, whether it would be folded by the end structure, whether it would be folded by the middle structure, and many of the things. What should be the size of the structure which should be sufficient enough to fold, or what should be the size of protein which it can fold? Many of the things it can be looked. So let's say if we simplify that system, so this is particular diagram of this particular host, which are called as chaperones. Simply, we try to model that structure using a capped carbon nanotube, similar kind of structure, and very basic format of protein. We took it as an alkane. Again, that's a very so we try to formulate an analytical method using molecular dynamic simulation, and then that can be explored further for particular application. Okay. So that's a basic structure that we try to explore. Okay. So that's a correlation between chaperones proteins host case, capped CNT alkane host case conformational analysis. Okay. The basic system again we use generalized amber force field, capped carbon nanotube, and alkanes water model simulations performed at similar conditions. In total, 36 simulations were performed where we had combination of 3 alkanes, 3 CNTs of different lengths, 4 CNTs of different diameters. So in total, 3 into 3 into 4, 36 simulations were conducted to check what is the impact on resulting self-assembly. Okay. So all simulations resulted into basic 2 criteria. First one, either it formed a capsule. Second one, it didn't form the capsule. So first table, so that particular table shows like here you have short CNTs, mid CNT, long CNT. That's the length of host molecule. 13-0, 14-0, 15-0, 16-0, that's the diameter of host molecule. And the N-dodecane, hexadecane, icosane, that's a host guest molecule. Okay. So if you look at a basic thing, then when you have a longer CNT and a shorter alkane molecule, what happened? That particular entire alkane molecule got engulfed into single CNT. So there was no capsule which was formed, and there was a single capture in the single CNT. Okay. So for such combination, there was no capsule formation. Similarly, when you have a shorter CNT, a shorter alkane, and a larger and longer CNT, there was no capsule formation. That was the first observation that we obtained from the simulations. Okay. Then we performed certain analysis. Like as we said, our major force on this particular analysis was to conformational analysis. How exactly the conformation of substance changed when it goes inside those particular capsule. That was our major motive of the analysis. So these are the different analyses which we have performed. So I will show them one by one. So the first analysis was the trans and Gauss conformation. So if you know what are the conformations, so if you have opened molecule, these are called trans conformation. And if you have the closed molecule, like let's say the bulkier structure are segregated at a distance, these are called trans structure. And if you have bulkier structure in nearby each other, these are called as Gauss structure. That's the first analysis that we did. So if you look at this particular graph, these particular graphs show you the comparison of the alkanes when they were present in bulk, freely roaming around, and when they are captured inside the capsule. So these are for three different alkanes. First one, this is for the shorter alkane. Now, obviously, when there is a shorter alkane, so it has space to get relocated inside the capsule. So what happens? Shorter alkane opens up itself, and you can observe that it has high probability of 180-degree angle. That's a trans angle. So it's a opened up structure. Then when you have slightly longer alkanes, they don't have space to open up. So they get coiled. So you have more of the Gauss conformation. That's a very basic observation we can conclude from this particular analysis. Now, if you change the guest length, so let's say you have the three different guests, then you can conclude that when the guest is smaller, it is free to move. When guests are longer, they get configurationally locked. Very, very obvious observation, like because there is no space for longer guests to move inside, obviously it would be locked. Okay. So that's a very obvious observation for the specific size of the host. Then so this particular analysis for the entire thing. Now, okay, as we said, we are into materials development. Now, and our main motive was not to simply have conformational analysis, but we need to know, okay, we are saying like for a longer alkane, it would be coiled. Now, next question arises from where it would coil, whether it would coil at the end, whether it would be coiled in the central portion. So, and then we can correlate with this particular thing in the structure of molecule which we wish to encapsulate within that particular host. Let's say there is a certain molecule which cannot be twisted at the end. And if we found like, okay, it can be only twisted at the end, we cannot use that particular combination of host case for nanodrug delivery. Okay. So this particular kind of analysis, individual dihedral analysis, can help you correlate with those particular answering of those particular questions. So just an example, like let's say if we consider the shorter dodecane molecule, we observed for all of its conformation, it had trans conformation. So like it's a entirely opened up molecule. If we consider hexadecane, the central portion of the molecule remained trans, but at the end it started to coiling. Okay, so it was not the case like it coiled in between. It coiled because of the end structure correlation. Icosane molecule, because it's a very long molecule, it coiled throughout. So you can see entire Gauss conformations of this particular molecule throughout the structure. So now you can have the idea as to what length of molecule can be folded in what range of host molecule. Okay, so that was a basic analysis. Then if you know the basic biological thing in terms of protein, there are very specific contours which are called Ramachandran plots. So we slightly try to correlate our observation with those graphs which are called as Ramachandran plots. These are 2D contours and these are consecutive dihedrals analysis. These are very specific to protein analysis, and we try to correlate it with those. But this particular analysis correlates very well with the individual dihedrals also. So if you have very extended configuration, there are angles which are having 180 degrees. So you will find only the contour in the center. While for other coil structures, you will have other contours which belong to Gauss trans conformation also. Okay. Okay, so that's again a similar observation, which is very similar in terms of the individual dihedral analysis. So that was the impact of guest length. Now let's say you have the host length which is varied. Again, when you have a longer host, it can accommodate more of the guest. So you will have a rapid conformational equilibrium or free to move structures. While for smaller host, you will have smaller or locked structures. Okay. Similarly, for the diameter, if you have a larger host, it can freely accommodate guests. And if you have a smaller thing, it would be a log structure. So many of the obvious things, but again, the mode of analysis or the way of analysis is what we were trying to establish and which can be then reperformed for the very applicable molecules. Okay. So another thing which can be obtained was to then plot those particular things in terms of percentage. So you have guest length impact on the trans percentage, host length, and the host diameter percentage. So obviously, as the guest length increases, your trans percentage decrease because it would be a coil structure. Similarly, for host length, as host length increases, trans percentage increases because it's an uncoiled structure. And similarly for host diameter. So trans percent dihedral energy change, which is directly related to coiling. So more of the coiling, more of the dihedral energy change would be obtained. Then it would be CNT alkane van der Waals interaction. Now again, if you look into energetics of this particular assembly, what is happening when your alkane is getting inside cap CNTs, basically it is trying to hold CNTs. That's one way of looking at the association. So when that particular alkane is trying to hold the CNTs, the interactions of nature of interactions would be van der Waals because your carbon nanotube is an uncharged structure. Okay, so there won't be any Coulombic interactions. The sole interactions would be van der Waals interaction between CNT and alkane. Okay, so CNT alkane van der Waals interaction, when you increase the guest length, obviously there are more favorable interactions. Host length doesn't have that impact because like guests are not sufficient enough to increase those particular interaction. And again, host diameter, as you increase, more and more guest can coil around the host diameter, and then you can have the host diameter impact on the resulting interactions. And final analysis was the water excluded contribution to the capsular assembly. First thing that is happening, alkane holding the structure. Second thing that is happening, your CNT also holding another CNT. So your net capsular assembly results from three different contributions, like the CNT interaction and the alkane interaction. So that's an entire interaction that we try to correlate. And it was almost similar to the CNT alkane interactions. So in terms of, again, our theme materials development, this particular kind of analysis can be very useful in terms of development of novel materials. So like you know what happens to the conformation and you know what happens to the energetics. So you design certain material and then target its particular this kind of analysis, and you can be predicting about the resulting properties. Okay. So again, that's further analysis in terms of conformation that can be done, and solvent accessible surface area. So when you say solvent accessible surface area, basically that's how the solvent excludes from the host and guest. Okay. So that can be again analyzed further. So there are certain conclusions which I already explained, like it's an irreversible assembly which is formed. And then depending on the size of host gas, you can either have a conformationally equilibrated structure or it can be a locked structure. Both of them are possible, and energetics of this particular structure. Third project, interesting project, which I did, that was based on encapsulation of cholesterol inside a carbon nanotube. Now, if you look at this particular study in terms of material development, let's say you are designing a biosensor. Now in biosensor, the basic principle of biosensor is to identify specific molecule and give either its presence or absence, or give either of its concentration. Any of these two things are the use of biosensor. So first thing that it should do, it should identify certain molecule, it should capture certain molecule, and then either it can simply give absence or present, or it can give you the quantity which is present. So or it could be other a capture device, like very nowadays the cholesterol increases the major what we can say issue in terms of health. So let's say, can we design a certain device which can capture cholesterol and remove, like similarly other molecules. So with those particular theme in mind, we did certain basic simulation in which we tried to capture cholesterol in a carbon nanotube. So a very basic or a routine problem with age atherosclerosis, your arteries get choked with cholesterol. So let's try to find out certain mechanism. Can we have a carbon nanotube similar structure for removal of cholesterol? Is it feasible? That's a question, and we try to answer. So cholesterol molecule, we know now. Again, if we correlate it with the theme, what are the thoughts that we would obtain when we try to devise such kind of material? First, we should be aware of what nature of molecule we are targeting, because like cholesterol being a non-polar structure with a certain polar group, it would need a specific molecule to capture that. It cannot be captured with any of the, let's say you put in a polar molecule, it wouldn't be captured because its majority of the structure has a non-polar nature. So the nature of molecule again would be playing role. So if you, let's say, design a biosensor, you will need to have certain such kind of sensing molecule which would be correlating with the molecule which needs to be sensed. So that's a cholesterol molecule which is having a hydrocarbon tail hydroxyl group, majorly a hydrocarbon structure, can be used to be captured with the carbon nanotube. Okay, so our system here again comprised of general force speed, a CNT, cholesterol molecule, water, and solvated in water. So that's a snapshot which showed the cholesterol which was outside got inside the CNT. That's the first result that we obtained. But like, okay, that got inside. Now again, question comes up into the mind. Why is that molecule getting inside? Is it getting inside because of its CNT interaction? Is it because water is pushing it? Or what exactly is the role of individual things in that particular association? So again, we performed potential of mean force study, like the free energy calculations for this particular system. Like we drag cholesterol externally to inside carbon nanotube, and we observe what is the free energy change in the system. So we obtained, like, as the cholesterol molecule got inside carbon nanotube, your free energy of the system decreased, which means it's a favorable association. So let's say there was a certain other molecule, or let's say you had certain different molecule other than CNT, and if we try to pull that particular molecule, you may obtain that free energy change of the system is positive. Then you can be sure, okay, this particular combination of molecules is obviously not an good combination to be tried. So you saved your experimental timing. Like you need not to perform experiments on those two substances. You can simply on computer put those molecules, try their free energy profile, and if their association seems to be favorable, you can conclude, okay, this is a favorable combination. If not, you need not to perform experiments. So you can save a lot of experimental things if you have hold over computational technique. So that's the first result that we obtained. Okay, cholesterol goes inside carbon nanotube with a strength of 43.26 kilocalorie per mole. Further question, what is driving that particular assembly? So we segregated those particular associations. So direct cholesterol CNT, again, that's a favorable thing, while water is trying to oppose that particular association. So now if you look at the molecular level, what is happening, if we had a simple CNT which is solvated in water, there were water molecules which were present in the surface of CNT and inside the CNT. Okay, now when that cholesterol molecule goes inside the carbon nanotube, first thing that particular molecule needs to do is to remove the water molecules from inside the carbon nanotube. Okay, then it would be possible for cholesterol molecule to enter inside the carbon nanotube. So these are the things which are happening at the molecular level. So if we explore thermodynamics of this particular process, like what is happening to free energy, what is happening to enthalpy, and what is happening to entropy, then we can see. So like many of the those who are having mechanical engineering background, I suppose they know like how do we. So that's a Gibbs free energy, entropy, and enthalpy. So basic correlation H is G plus Ts. And from free energy, we know the value of G. And then accordingly, by eliminating H at constant pressure, we can find out the entropy. So that's a thermodynamic contribution which we are trying to explore. So we performed the similar simulation at 3 different temperatures, and then using the particular gradient, we found out what are the thermodynamic contribution of this particular association. Okay. So what we obtained, like entropically, this particular phenomenon is not favorable. Okay, so that's a positive value of minus T delta S, which shows the delta S value to be negative. And we know like entropy should increase, which is a natural tendency of any system. Like if you have increase in entropy, it would be a what we can say, it would be a favorable phenomenon. But this is not what we observed. We observed it's an enthalpically driven phenomenon. Now, if you change the solvent, if you change post case, again, these particular terms would be different. So for that particular association, thermodynamics would be different. Now you can see experimentally, it would be very tough to identify these particular things. But using simulation, these things which are very important are getting very easily achieved. Okay. So that's what happens when the water molecules, they get removed as the cholesterol enters. So this particular graph shows as cholesterol molecules are entering inside the CNT, water molecules are getting eliminated. That's a calculation that we showed. So if you, let's say, if some of you are experimentally, so it's not the case like experiments don't have, they have very own things like the computationals are verified using experimental observations, and using those then observations you can generalize them. So it's not the case like experiments doesn't have any role. Obviously experiments are the first things which is it's a natural thing. So I'm just explaining the computational techniques which are having role in today's thing. Okay. So these are certain conclusions very specific to cholesterol. Okay, CNT can be used for cholesterol capture, basically driven by van der Waals interaction, opposed by water-mediated interactions. So it's an enthalpy-driven phenomenon and unfavorable entropic contribution. The reason being the water molecules are getting eliminated, which were very disciplined inside CNT. They were forced to go into the random bulk. And again, that's unfavorable entropic contribution. Okay. So that's the third project. Two more projects. Again, I will scroll through because it's already 7 o'clock. I will try to end my presentation in 10 minutes and then we can have certain discussion. Now, polylactic acid molecule, if you have heard the term, very relevant to environment because plastics are non-degradable. So there is demand of materials which are biodegradable. And one of the important material in terms of those things is a polylactic acid. So it's a polymer of lactic acid, biodegradable polymer. So if you are into, let's say, biodegradable materials development, polylactic acid would be the first choice. So here in this particular study, we chose different solvents and saw what happens when polylactic acid gets assembled in those particular different solvents. Okay, so we looked at the different enantiomers of polylactic acid. We chose certain functionalization. We chose certain combination of solvent, and we looked at what happens to the self-assembly. So behavior of PLA in self-assembly. And stereocomplexation is another phenomenon. Like, let's say there are different enantiomers D and L, how they mix, what happens. So that's a very important phenomenon in terms of self-assembly, because let's say you have different conformation, they are easy to self-assemble. So that's what we explored. So again, as I reiterate, I will try to explain certain results very specific to this particular system, but what it would be great to take away is what's the role of simulations in this particular analysis. Okay, so these are the combination of solvents that we chose. That's a study. So 1 nanosecond equilibration, 10 nanosecond production. These are specific to molecular dynamics simulation, and temperature, room temperature, pressure, normal 1 bar pressure, and force field name being OPLS A force field. Now, the kind of analysis which would be guiding the role of solvent, first analysis is radius of gyration. Now, when we say a molecule and when we are trying to look at its resulting configuration inside a solvent, we first think that we observe whether it is opening up or whether it is a closing up. So closing down. So that is guided by radius of gyration. So if you look at the result in acetone solvent, PLA molecule opened up a very largely. What are the reasons that are again explained in the following slides? Solvent accessible surface area, again, the molecule which is open has higher surface area. So again, higher for acetone, trend almost similar to the radius of gyration. Second, radial distribution function that we try to explore. Okay, so polylactic acid molecule and solvent, how exactly they are interacting, like what portion of polylactic acid is actually getting attached to the solvent molecule. So now we have different 5 solvents, let's say water, acetone, benzene, and methanol, and tetrahydrofuran. Now, these are very large molecules, but those molecules get attached because of certain functional groups. Like if you consider methanol, it has OH group. And if you consider polylactic acid, it has again OH group. So there are polar groups, there are non-polar groups. So this particular radial distribution function shows how exactly those particular molecules are getting attached to what portion of polylactic acid molecule. Now, let's say you are an experimentalist and you wish to explore certain solvents which for their feasibility and non-feasibility in terms of polylactic acid. So first thing you can do is to simulate those systems and observe what are the radial distribution function, what are the different criterias like the solvent accessible surface area, radius of gyration, and you can have a first-hand knowledge. Okay, whether is this a solvent very useful to be used for this particular thing, or it's not very useful for the further application. Okay, then the second thing that we tried was to end functionalize polylactic acid. So there is a crude polylactic acid, and you can then functionalize its certain portion to have their novel properties. And if you look at the radial distribution function, it changes drastically. So with a slight change in the molecular level structure, you can have large change in terms of its property. Okay. So that's the new term that we coined. So that's why I'm terming it to be a novel term. We called a stereo complex favorability index. As I said, stereo complexation is important phenomenon in terms of enantiomers. So you have here D conformation and L conformation, and this particular calculation shows how very well the different enantiomers of polylactic acid get assembled. So as we can say in acetone, your stereo complex favorability index is very low. So in this particular thing, your stereo complexity won't be of very good nature. And while at other two ends, it could be of very good nature. That's the basic thing that we did, again coming from the SASA. These are the snapshots of self-assembly. So again, you cannot observe them as they are in, like you can see the globule formation, or you can see they are in the solvated structure. But these are the exact things that happen. Like, so you can see, okay, what must be happening at the molecular level at different solvents when polylactic acid is there. Okay. Now, as I said, first thing, that's the geometry of solvent which can impact. Second thing, it can be what is the energetic which is driving. So basic two energies, van der Waals and Coulombic interactions, which would be driving their association. So we try to segregate the individual contribution. Now, let's say there is a larger molecule, it will have larger van der Waals interaction. Let's say it's a polar molecule, it will have more Coulombic interactions. And depending on their relative strength, then you can have their impact on the molecule which you are trying to study. So, like it's let's say if we consider this particular study in which we have the PLA and solvent, and so if we want to have what is the impact of van der Waals interactions, so that's a formula which we would be using, like we would be calculating van der Waals energy for entire system, and then we would be segregating individual van der Waals interaction. So that would be the net interaction between PLA and solvent. That could be the way of analysis. Okay, similarly for Coulombic interaction. Now, if you look at majority of the molecules, because they have a larger backbone structure, they have high amount of LJ interaction. But if you look at the water molecules, majorly it is driven by the Coulombic interaction. That's a general trend. In-depth analysis can be performed for different solvents. Like benzene, it's almost a LJ interaction because benzene is a non-polar molecule. It doesn't have much of the Coulombic interaction. So most of its interaction would be driven by LJ interaction, very small portion of the Coulombic interaction. These are certain observations which can be obtained using simulations. Okay. So certain conclusions which are very specific to this, you can have a read through them, or it's fine if you even if you skip those because they are very specific to this particular system. Crux, this can be replicated for any of the combinations which you are interested in. Last study which I would be explaining, it's an interesting study. If you look at its practical application nowadays, it's a very energy basic theme correlating it with the environment. And when we have this particular correlation of energy and environment, fuel cells come into role. So they take in hydrogen, deliver out water, very environment friendly application. So, but fuel cell are still in the phase of development. So, like when we say fuel cell, basically the materials are in the phase of development. If you have novel materials, if you have novel catalysts which can drive reaction and which are compatible, then it's a very good fuel cell. So again, it comes to the materials development. Now, how MD simulation or how computation can again be used in this particular materials development. So there is a solid oxide fuel cell which which is based on this particular principle of oxygen anion diffusion. I will show certain reaction, and if those particular reactions are to be proceed, your oxygen should be diffusing very fast through the electrode. Now, how do we enhance that oxygen diffusion? That can be done by creating artificial vacancies in the electrode. So you create different amounts of vacancies, and then your oxygen moves faster, and the current gets faster. Current gets generated then faster. Not a very simplistically, I am trying to explain. There are in detailed complex phenomenon which happen. So this particular project, I would be trying to show how the recent artificial intelligence and machine learning techniques can be embedded in the molecular dynamics simulation for advancing very specific electrode development. It can be applied for many of the domains. I will show you one of the specific domain which I have worked upon. So that's a basic principle of solid. That's a basic structure of solid oxide fuel cell and perovskite material, which I have tried to check. So perovskite materials are normally used. So these have the structures of strontium titanate, strontium being A-site material, and titanium being B-site material, AbO3, a general formula, and we artificially create the vacancies at A site. Okay. So what is solid oxide fuel cell? You can go through a general reaction. There is an oxygen anion which gets generated at the cathode, and that needs to be traveled upon. So our objective was to enhance their diffusion. So our system was so objective to now, okay, so that needs to be diffused upon. Now that particular motion when it diffuses and there is A site deficiency, so what we tried to address was looking at that particular structure, looking at A site deficiency. So what are the different phenomena which guides their motion? Okay, so what's the impact of vacancies on their motion? So that's what we try to observe using molecular dynamics simulation. So first we took a crystal, we ran simulations and we allowed oxygen to move through it, and then we tried to model the motion or the location of oxygen ions using machine learning techniques. So the very simple technique which is called as Cummins clustering. It's a supervised learning technique, right? So if I'm correct, yes, it's a supervised learning technique. And K-means clustering. So basic technique in machine learning, like let's say you have a data and you wish to cluster in three different domains. So it is unclustered data and you cluster it. So that's a basic technique. That's what we did in terms of oxygen anion motion. Okay. So your oxygens are moving randomly and we try to cluster their motion, checking the impact of A site onto their motion. That was our objective. So again, that's a detail of methodology. This was done using Python coding. So you can see the materials development, which is a very, what we can say, a real phenomenon. We are trying to take it into the machines. So through coding, we are trying to address the what's happening to the materials. Okay, so that was done using Python code. That's a methodology to be done in terms of the clustering. So the basic here comes the results and discussion. So we as I said, we artificially made A site vacant of percentage 5%, 10%, 20%. And the basic calculation which guides the motion is mean square displacement of oxygen ions. And we observed it to be highest for 5% vacant structure. Okay, based on mean square displacement, we calculated diffusivity. Obviously, it's highest for 5% structure because it's obtained from the previous graph. So I'm scrolling through these because I want to show certain applications in terms of machine learning that we obtained. So that's the oxygen density profile, how oxygen exactly moves in those particular structures. So more the vacant structure, obviously it would have more space to relocate and it would be moving more rapidly. Okay. A natural question comes, if it's a more vacant structure, why does 5% have highest diffusivity? So that's the question which should be answered, but that's not a very simple to answer question. There are multiple phenomena which needs to be addressed. Like 5% structure have more number of oxygen. That could be the first answer. 20% structure has less number of oxygen, because if you are removing A site, we obviously have less number of oxygen to balance the charge. So this question may seem to be simple. Okay, 20% has more of the density profile, so it should have more MSD. That's not the case. It would be a very complex phenomenon. That's a certain superficial observations which we are looking at. Okay, so that's the oxygen density profile. It's simply obtained using molecular dynamics simulation. How exactly is oxygen moving through the structure if we look at that particular structure from the top? Then here comes the machine learning part. So if you look at the previous graph, it's simple projection of the location of oxygen, and then those particular locations are then mapped into clusters. Okay, so when we say initial and learned cluster centers, learned oxygen centers, so basically more is the deviation from initial oxygen center to learned, more can be the diffusion of the oxygen. That's a very basic conclusion which can be drawn from this particular graph. Okay, then the next analysis are further analysis of those particular things. So when we say cumulative oxygen in cumulative intercluster oxygen jumps, that means in that particular location, how frequently your oxygen is staying. So the basic observation states that more the vacancy, more would be the leap counts. That means more would be the motion of oxygen. That's a very basic observation. Now, further analysis, that's the number of intercluster oxygen jumps for individual atoms. So now, okay, that's a bulk phenomenon that we observed. We calculated what is diffusivity, but that bulk diffusivity needs to be addressed from individual atoms analysis. So this particular analysis then we did for checking the oxygen jumps of individual oxygen for different vacancies. So here we obtained for larger amount of vacant structure, the oxygen jumps were very high. That means it had possibility to move because of the vacancy. That was second analysis. Then initial and learned oxygen cluster center differences. Okay, so as the vacancy increases, what's the amount of dislocation in the cluster center? So if you look at the particular graph, so in 20% efficient structure, there are more oxygen empty sites distributed throughout the structure, which leads to a wider range of oxygen dislocations in different proportions. So if you look at this particular graph, for 20%, it's a very high structure as the length increases, while for smaller 5%, it was higher for the lower displacement. That's an observation. Okay, then residence time distribution of oxygen ions, this particular. Now, when we say oxygen ion motion, first thing, how long it moves. Second thing, how fast it moves. So when we said the displacement, it showed how long it moves. And when we say the residence time, it shows how fast it moves. So let's say residence time is smaller. It means it is moving very faster. So if you look at this particular thing for the 20% structure, it has very small residence time. That means it has large motion in 20%. So oxygen ions are less mobile in terms of residence time for lower acid diffusion complexes, indicate that they're strong at cluster sites for longer periods of time before jumping. That's the observation. Now, all those things you cannot predict simply using experimentation. You obviously need certain insights of the system, and which can be again obtained using molecular dynamics simulation. Cumulative displacement of the oxygen, how long this particular oxygen can move, I will try to briefly cover. So almost we are at the end. And again, that's a cumulative displacement of individual oxygen ions. So observation implies that higher degree, more space available for motion. And so again, if you look at this particular graph, for 20%, the displacement rates are much more higher, while for the 5%, the smaller displacements are there because there are less vacant structures which are available. And displacement amounts of oxygen for individual time step. Now, okay, oxygen is moving, but for individual time step, how much it is moving, and in bulk, how much it is moving. So that's the individual type step displacement amount for oxygen. So greater differentiates lower migratory barriers and allow oxygen to go farther in the dislocation. So if you have very small vacancies, obviously you cannot have longer jumps. So if you look at the 5% peak, it's there for the smaller displacement. And if you look at the green peak, it ranges from minimum to the maximum. So for higher higher vacancy, you can have longer jumps. That's a displacement amount which is possible. So there are certain conclusions which are summary of what those particular graphs showed and very specific to that particular project. I will just summarize what could be the key takeaways, because this particular faculty development program has a theme of materials development in 21st century. I try to address what are the role of computational tools in nanomaterials development, especially in the era when we have very good computational facilities, supercomputers available. What's the role of computational tools? So these are indispensable in driving advancements in nanomaterials. And so if you look at the kind of analysis which is being done, so you do have experimental analysis. In addition, you do have simulation analysis. Nowadays, that's a trend which is being followed. Molecular dynamic simulation out of different techniques. I have my own experience in molecular dynamic simulation. So I try to explore certain case studies which are very relevant to the topic of this particular FDP. I briefly mentioned about other computational techniques. They have their own utility and they need their own expertise. And finally, certain case studies which I try to show how molecular dynamic simulation can give you the wide range of analysis starting from free energy, thermodynamic, conformational analysis, and very applicable to different domains, chemical engineering, mechanical engineering, materials development, very widely applicable technique. And the recent AI and ML, that's how these two things can be embedded, the molecular dynamics along with the AI ML, machine learning or data techniques, because it's a simulation, you have large amount of data which is available. And these two techniques can be further embedded and can then further give you the enhanced results and can be again used for materials development. So that's all from my side. I hope I ended in time. It's a 7:20. We do have 10 minutes. So in case if there are certain questions, please ask. We are all faculty, so I will try to answer whatever I could, and I will try to gain from whatever the questions you ask. So you can ask questions, whatever things are there. So that's from my side.
Thank you, Dr. Gade. Now I request participants to unmute themselves and you can ask the questions. Dear participants, you can unmute yourself. You can unmute yourself and you can ask the question. Am I audible, sir?
Yes, Prasanna, you are audible. So if there are certain questions you can ask. So maybe like because we all come from different expertise, so I may gain something new from those expertise, or if I could contribute something, I would be happy. Anything is fine.
May I?
Yes, there's some question.
Dr. Pratibha.
Yes, thank you, Rishikesh Sirji.
Ma'am, your voice is low, ma'am.
Yes.
Actually, session was very nice. Little bit means it's a very tech touch, means engineering touch. According to that, basically I am from physics. I have just that particular question with the thermodynamical base because you many times repeated that particular thing, thermodynamics, the entropies, free energies, isn't it? By
Yes.
machine learning or simulation, you can calculate. How we can go that particular things practically? Is it possible? Means we can calculate that free energy, enthalpy, or entropy in a simple manner. Because by machine or simulation we can do that, but
Yes.
it is not my expertise. So a little bit, it was very means it is very new for me, isn't it?
So even that's not my expertise, like experiment, but when I was performing these things, I heard from some of the professors, like there are certain devices which can calculate free energy change. That's what I heard from my professors when I was doing my doctorate. But again, that's not my expertise. My expertise is again simulation. But for sure, entropy, I don't think we would be again calculate. It would be possible because entropy is an non-calculable phenomenon. So, like even if we go for direct calculation, we do it by Q by T. So we need enthalpy, and based on that, we calculate entropy. But for free energy change, I suppose there are certain techniques or tools which can calculate. So if some of us is having any experience, they can also share. I'm again not expert in experimental calculation. That's what I know.
Okay, thank you, Suji.
Yes, if anybody is having expertise in that knowledge, can please share. So that would be helpful for all of us.
Yes, sir. Similarly, from my side, because it's a very kind request. Whoever that particular expertise, please share. Because it's very important, sir. Once means you people are a very tech touch, means that particular simulation from your side. If anybody is there who can perform that practical or had performed that practical already, then really it will be a very good blending. I think so.
That's correct. Using simulation, you can comment upon favorability, non-favorability for sure. And that should be okay experimentally. So, but yes, experimental validation, if it is done, that would be very good. That would be the best.
Sir, nowadays means we are going with that particular SWNT and MWNT. It's very means crazy field. We can go with practically means practically we can go with that particular topic.
Okay. Yes, yes. Yes, CNT has always been a good material and it's a novel material having wide application in all domains. So when we try to took that project, when we were going through literature, literally in every field, carbon nanotube is having their application, and still it's one of the very widely used material.
Any other questions from other participants? I think we should stop here, right?
Yes. And I am open for any questions, collaboration. You can write to me on my email address available on the website. If there are any possible collaborations or anything, again, I am very happy. So please feel free to contact me. My email is available on my website and I would be available. I would be happy to contact anyone. So, okay, Prasannaji, thank you. Thank you very much for this opportunity. So we have around 110 participants. So I could convey my message to 110 people that, so thanks again for this platform.
Definitely, sir. Thank you. Thank you, Rishikesh Gade, Dr. Gade, sir, for taking a time and sharing your expertise with the participants. On behalf of Cummins College, once again, I thank you. It is a very nice session because nanomaterials, since many years, we are working in the many researchers, they are working in nanomaterials, but the simulation part is something advanced and new. And you have explained it through, real-time case studies. And that's very important. That was a good part of this presentation. And once again, I thank Dr. Gade for this